Hello everyone, welcome back to my channel. This video is the continuation of the harmonic functions video, that is part 1 video. Okay, so in this part 2 video we will solve the same problems. That is, in the last video we have discussed about how to find the harmonic conjugate of the given function. Okay, so if you want that video, whose link is given in the description box, okay, you can go through it. Now let us solve the next problem. Show that u is equals to x cube minus 3xy square is harmonic and find its harmonic conjugate. So for this, first we have to show that the given function is harmonic, then we can find the harmonic conjugate of this one. Okay, u is equals to x cube minus 3xy square. Let us consider this function as equation 1. Okay, so now differentiating this partially with respect to x and y, we get, so partially with respect to x we get x cube differentiation is 2x square minus here y square being constant, okay, 3y square constant, x differentiation 1. Similarly, dou u by dou y is equals to x cube being constant, okay, so minus 3x constant, y square differentiation is 2y. So that is, we get minus 3 into 2, 6xy. Consider this as equation 2. That means these partial derivatives we consider together equation 2. Now again differentiating these two partially with respect to x and y, we get, so this implies that dou square u by dou x square is equals to, so differentiating with respect to x we get 2x square differentiation is 2 into 2, 4x, this being constant, therefore differentiation is 0, and dou square u by dou y square minus, because we are differentiating with respect to y, 6x being constant and y differentiation is 1. Consider these two equations, that is partial derivatives equation 3. Now sorry, here it is 3x square, right? 3 into 2 is equals to, we get 6x. Now from this equation 3, it is clear that, or you can consider dou square u by dou x square plus dou square u by dou y square is equals to 6x minus 6x equals to 0. That is, dou square u by dou x square plus dou square u by dou y square equals to 0, which implies that u is harmonic. Okay, so first part we have proved this one. Now let us find the conjugate of v, that is harmonic conjugate of v. So for that, the first step is, first we have to consider, that is, let v of x comma y be harmonic conjugate of u. Okay, so then in the second step we write total derivative of v, that is dv can total derivative of this v can be written as dou v by dou x dx plus dou v by dou y dy. Now we replace these partial derivatives in terms of u, that is minus dou u by dou y into dx plus dou u by dou x into dy. These are from the CR equation, by CR equations. So by the CR equation we have dou u by dou x equals dou u by dou y and dou u by dou y equals to minus dou u by dou x. So from that we can substitute this one, because these are known, that is by the equation 2 we can substitute those values, that is dv is equals to minus dou u by dou y. Dou u by dou y is this one, minus into minus we get plus 6xy, that is plus 6xy into dx plus dou u by dou x is 3x square minus 3y square. 3x square minus 3y square into dy. Now it is of the form m dx and n dy. Okay, so therefore here we get m is equals to 6xy and n is equals to 3x square minus 3y square, and solution of this equation is given by. So if you want to know each steps, that is how to find the harmonic conjugate step by step, you can watch the part 1 video of this harmonic conjugate. Okay, that is harmonic function. So whose link is given in the description box. You can go through it. There you will get the complete idea about the harmonic conjugate of the, that is how to find the harmonic conjugate of the given function. Okay, now so solution of this function, that is solution of m dx and n dy plus n dy equation is given by v is equals to integration of m dx treating y as constant plus integration of terms of n not containing x into dy. Okay, so now, so therefore v is equals to integration of m dx. We write terms of m, so that is integration of 6xy dx, but in this case we have to treat y is equals to constant plus integration terms of n not containing x. So terms of n not containing x means only this term, but this term contains x. So along with the sign we have to write. So thus here it is minus 3y square into dy. Okay, now integrating we get, so here we have to treat y constant, so therefore 6y taken outside, x different integration is x square divided by 2. So minus 3 y square integration is y cube by 3 plus c. So here we get this 3 get cancels. V is equals to 3yx square minus y cube plus c is the harmonic conjugate of b, given function u. Okay, next problem. Show that u is equals to e raised to x sin y plus x square minus y square is harmonic and find its harmonic conjugate. So here given function is u equals to e raised to x sin y plus x square minus y square. Okay, consider this as equation 1. Differentiating partially with respect to x, we get dou u by dou x is equals to e raised to x, differentiation is e raised to x sin y constant, and x square differentiation is 2x minus y square differentiation 0, and similarly dou u by dou y is equals to e raised to x constant sin y differentiation cos y plus x square differentiation 0 minus y square differentiation 2y. Consider this equation 2. Now again differentiating with respect to x, dou square u by dou x square is equals to sin y, again constant, e raised to x differentiation e raised to x plus 2x differentiation is 2, and dou u by that is dou square u by dou y square, that is differentiating with respect to y, we get cos y differentiation is minus sin y. So therefore e raised to x constant, we get minus e raised to x sin y minus 2y differentiation is 2. Now we consider dou square u by dou x square plus dou square u by dou y square is equals to e raised to x sin y plus 2 minus e raised to x sin y minus 2. So consider this equation as equation 3. So now, so cancelling this, we get equals to 0. Thus u is harmonic. Okay, now we have to find v, that is, let v of x comma y be harmonic conjugate of u of x comma y. So thus dv is equals to dou v by dou x into dx plus dou v by dou y into dy. So by the CR equation, this can be replaced by minus dou u by dou y into dx plus dou u by dou x dy. So this is by CR equations. Okay. Now therefore dv can be written as minus dou u by dou y value we substitute from the equation 2. It is equals to e raised to x sin y plus 2x. So minus e raised to x sin y plus 2x. Sorry, first we have to substitute dou u by dou y value. Okay, so it is e raised to x cos y plus 2y. It is minus, but minus into minus we get plus 2y into dx plus dou u by dou x value is this one, e raised to x plus 2x, that is e raised to x sin y plus 2x into dy. Now it is of the form m dx plus n dy equation, that is exact equation form. So therefore solution of this exact equation is given by v is given by integration of m dx treating y constant, okay, plus integration of terms of n not containing x terms, right, not containing x into dy. So those are integration. M means this completely, you can write here m is equals to minus e raised to x cos y plus 2y, and n is equals to e raised to x sin y plus 2x. So that will be easy to you. Okay, so first we write terms of m all, minus e raised to x cos y plus 2y into dx. So treating y constant, okay, plus terms of n not containing x. So here we have to find terms of n which are not containing x. You can observe that both terms contains x, therefore we write here integration of 0 into dy, which will be totally 0. Okay, so therefore we have to integrate only this term. So got this one. If n doesn't contains any terms which are independent of x, then we have to take 0. Okay, so therefore v is equals to minus taken outside, integrating with respect to y, sorry, with respect to x, treating y constant, we get cos y being constant, e raised to x integration e raised to x only, plus 2y is constant, therefore 2y into x integration, sorry, 1 integration is x plus integration constant c. Thus this is the harmonic conjugate of the given function, which is required harmonic conjugate. Okay, show that u is equals to sin hx cos y is harmonic and find its harmonic conjugate. Solution: given function is u is equals to sin hx cos y. Differentiating this, we get dou u by dou x. First let us consider this as equation 1. Now dou u by dou x, differentiating with respect to x, cos y being constant, sin hx differentiation is cos hx, and dou u by dou y, sin hx constant, cos y differentiation is minus sin y. Okay, consider these two equations as equation 2, and dou square u by dou x square, that is double differentiating this one, we get dou square u by dou x square, again differentiating with respect to x, we get now cos y again being constant, cos hx differentiation is sin hx, and dou u by dou y square differentiation is minus as it is. So sin y, sin hx as it is, sin y differentiation is cos y. Consider this as equation 3. Now consider dou square u by dou x square plus dou square u by dou y square is equals to, substituting values, we get cos y into sin hx minus sin hx into cos y. These two get cancels, we get equals to 0. Hence we can say show that u is harmonic, because we are getting these two equations equals to 0. Therefore u is harmonic. Now to find harmonic conjugate of u, let us consider v as a harmonic conjugate of u. Now dv can be written as, that is total derivative of v is equals to dou v by dou x into dx plus dou v by dou y dy. This can be replaced by the CR equations, that is minus dou u by dou y into dx plus dou u by dou x dy. So this is by CR equations. Okay, now therefore dv can be written as, now substituting values of dou u by dou y, so dou u by dou y is this one minus sin hx into sin y, so minus into minus we get plus sin hx into sin y into dx plus dou u by dou x value is cos y cos hx, that is cos y cos hx into dy. Again it takes m dx and n dy, that is plus n dy form. So here m is equals to this one. Okay, here m is equals to sin hx sin y, and n is equals to cos y cos hx. Okay, now we use the formula for the exact equation, that is we have y is equals to integration of m dx, treating y constant, plus integration of terms of n which do not contain x, terms of n which are not containing x terms into dy. So first we substitute m value, that is sin hx sin y into dx plus, so here we have to treat y constant. Now terms of n which do not contain x terms means, so you can observe that it has only one term and which contains x term, so it means here we have cos hx, so therefore we consider this as 0. or you can take integration of 0 into dy. So therefore integrating we get y is equals to, so integrating with respect to x, treating y constant, we get sin y into sin hx, that is sin hx integration is, it is sin hx integration is cos hx into sin y. Okay, so this is the required, which is required harmonic conjugate of u. Next problem. Show that u is equals to 1 by 2 log of x square plus y square, where x is not equals to 0 and y is not equals to 0 is harmonic, and find its harmonic conjugate. Okay, given u equals to 1 by 2 log of x square plus y square, differentiating this with respect to x, we get dou u by dou x is equals to 1 by 2. So log of x square plus y square differentiation is 1 by x square plus y square into x square differentiation is 2x. 2 to get cancels, we get x divided by x square plus y square. Similarly dou u by dou y we get the same way, we get, that is 1 by 2 taken outside, 1 by x square plus y square into y square differentiation 2y, we get dou u by dou y value is equals to y by x square plus y square, and dou u by dou x value is equals to x by x square plus y square. So consider these two equations as equation 2. Again differentiating with respect to x, we get dou u by, that is dou square u by dou x square, we get, so it takes u by v form. For that we write denominator as it is, that is v as it is, differentiation of x is 1 plus, minus, now x as it is, differentiation of x square plus y square with respect to x is 2x, because y square differentiation is 0, divided by denominator square, that is x square plus y square whole square, which is equals to x square plus y square, here we get minus 2x square. So here we get minus 2x square, minus 2x square plus x square equals to, we get minus x square, that is we get y square minus x square. So after simplification we get y square minus x square, denominator x square plus y square whole square as it is. So similarly we get, that is dou square u by dou y square value, dou square u by dou y square is equals to, again same, here also we have to apply u by v formula, denominator into differentiation of numerator minus numerator as it is, differentiation of denominator, so that is 2y divided by denominator square. So simplifying, here we get minus 2y square plus y square, we get minus y square, that is x square minus y square divided by x square plus y square. Consider these two as equation 3. Now we have to show that the given function is harmonic. For that we consider Laplace equations, that is consider dou square u by dou x square plus dou square u by dou y square is equals to y square minus x square divided by x square plus y square whole square. So dou square u by dou x square value plus x square minus y square divided by x square plus y square whole square. So here we have to get y whole square. So simplifying this one, taking LCM, we get x square plus y square whole square, numerator becomes y square minus x square plus x square minus y square, get cancels, we get 0. Therefore we get dou square u by dou x square plus dou square u by dou y square is equals to 0 implies that u is harmonic. Okay, now we have to find the harmonic conjugate of u. So that let v of x comma y be harmonic conjugate of v, that is u. Okay, therefore dv is equals to, we write dou v by dou x into dx plus dou v by dou y into dy. Now replacing this by the CR equations, we get dou u by dou y dx plus dou u by dou x dy. These by CR equations. Okay. Now substituting dou u by dou y and dou u by dou x values from equation 1. So that is by these equations. Okay, we get minus dou u by dou y. So dou u by dou y minus y by x square plus y square into dx plus dou u by dou x is x by x square plus y square into dy. Okay, so again it is of the form m dx plus n dy, m dx plus n dy form. Okay, so here m is equals to minus y divided by x square plus y square and n is equals to x divided by x square plus y square. Thus the solution is p is equals to integration y treating constant m dx plus terms of n not containing x terms, right, into dy. So first we write m dx completely minus y by x square plus y square into dx. Here we have to treat y constant plus, now terms of n not containing x means it is 0 because it contains x terms, so it is 0. Okay, so now integrating this one, we get v is equals to, we get integration of this one. So here we have to integrate with respect to x, treating y constant means we have to take y outside. Now it is in the form of 1 by x square plus y square. So y square means it is constant, so it takes of the form 1 by that is x square plus a square or a square plus x square form, which is equals to 1 by a tan inverse of a by x. Okay, so it is x by a. Now by using this formula, so here this can be integrated as minus 1 by minus y taken outside, 1 by x square plus y square integration is 1 by a means 1 by y tan inverse of x by y plus integration constant c. So y get cancels, we get v is equals to minus tan inverse of x by y plus c. So which is the required harmonic conjugate. So you can note this formula here. Okay, integration of 1 by x square plus x square is 1 by 8 tan inverse of x by